Chapter 7 is called the central limit theorem, and the first section, 7.1, is the central limit theorem for sample means. It's the one we're going to focus on. Central limit theorem, CLT for short, applies to the distribution, not of the random variable, but of the sample means of samples from the population. So the sample means is what this applies to. And I'm going to do a brief outline of the process to give you some context, and then we'll do some examples of using it in computation. So the word, or the phrase that I prefer is not the central limit theorem, but the sampling distribution. And the sampling distribution is that distribution of the sample means that I mentioned. It's in some ways similar to the original distribution, but in some ways superior, that we can use it. First of all, collect samples of size n, little n is the sample size, from the population, whatever that may be, with mean mu and standard deviation sigma, as usual. Now this is the mean of the population, and this is the standard deviation of the population. What we're going to look at, though, is the distribution of the sample means from these. So I'm going to put that as a separate step. Collect samples, compute the mean of each sample. So if we pick a random sample, it's probably not going to have exactly the same mean as the whole population. It's going to have its own sample mean, the mean of each sample. That's what we call X bar. It's a mean, but it only comes from the data in the sample, not from the data from the whole thing. So we compute a mean for each sample. And the third thing, I'm going to put a parenthetical statement here that this works provided the sample size is large enough. So we can't do this with like samples of size 2 or 3 or something. We need to have 10, 20, 30, big enough sample size. But provided the sample size n is sufficiently large, the X bars, because each sample has a different mean, but they're distributed in a certain way. The X bars will be distributed normally. That means we can use what we know about the normal distribution to do probability calculations. It doesn't say here that the population is distributed normally, and it doesn't matter. That's the value of this, is that we can, instead of looking at individuals, we look at sample means for different samples. We get a normal distribution, and that we can use. So I want to go over some notation before we get into the actual problems. I mentioned, and we saw this in chapter 1, I think, X bar is the mean of a sample, whereas mu is the mean of the population. The new notation here is for a random variable that has some distribution. We know there's a mean and a standard deviation for it, that's, as we saw before. This is the new one, X bar, so capital X bar is a distribution of the sample means, not the individual values, but the means of the samples I'm going to come back to this one with our normal distribution notation, but the new things are mu x bar. This is the mean of the sample means. That does seem a little convoluted. We're taking an average for each sample, and then we're averaging all of those averages. It's only 2 layers complicated, so it could be worse. But it's equal to the original one. We usually just call that mu, the mean of the population. If you want to be explicit about it, you can say the mean of the x variable. But here we're looking at the mean of the x bar variable, treating the sample means as a new variable. But the good news is it's the same. The mean of the sample means is the same as the mean of the population. Here's where it gets different. Sigma x bar. So the standard deviation of the distribution of sample means. So it's got its own symbol, sigma x bar. That's equal to sigma x over the square root of n, or sigma over the square root of n. You don't need to call it sigma x. Of course, it's the sigma of the x variable, the original one. It's the new one that's different. It's modified by dividing by the square root of n, which is the n is the sample size. So if we take larger samples, this number gets smaller. See, the denominator being larger means the number is smaller. So we're able to shrink the standard deviation. I want to put this together with, to really write something down for this. The distribution of sample means is what it is. Here's the consequence of the central limit theorem. I know I just got some new notation for this expression, and I'm putting the whole expression in there. I just want to emphasize that this is just the regular old mean, and this is the standard deviation divided by root n. The important part here, though, is that it's normal. The sampling distribution is a normal distribution, even though the original one may or may not be normal, or maybe we just don't even know. All right. I want to write down the name of this special quantity. We've seen one thing that's really quite new. I'm going to rewrite it and put its name there. It's the sigma x bar is the standard deviation of the sample means, also known as the standard error of the mean. So that's the full name of the thing, the standard error of the mean. I usually call it either the standard deviation of the sample means, because that's what it is, or sigma x bar. Sigma x bar is just that's what the symbol is, sigma x bar. So you can just call it that. I know it's a compound symbol, but so separate from the notation, something that I want to point out about the sampling distribution and the distribution of the sampling means is that larger n results in more normal. So closer to a perfect normal distribution. Larger sample sizes for our sampling distribution will get a more normal sampling distribution for the means. Now I have a note about the z-scores. In this case, z-scores for the distribution of sample means, z is equal to x bar minus mu over sigma over root n. It looks like a complicated formula, but it's really just z equals x minus mu over sigma, the z-score thing that we've done before. Here, though, I'm not looking at an x value, I'm looking at an x bar value, because we're talking about distribution of sample means. This is the same because the mean of the sample means is the same as the original population mean. And then instead of the standard deviation, I have this modified standard deviation, sigma divided by root n. So z-scores look a little bit different, but they mean roughly the same thing. So for some examples, to start with, let's look at example 7.1, an unknown distribution has mean 90 and standard deviation 15. That's the underlying original distribution of data. It doesn't even say how big the population is, just that the mean for that population is 90 and the standard deviation is 15. It also doesn't say if it's normal or not. Well, there's no telling. It's an unknown distribution. Doesn't matter. Because we're going to say samples of size 25 are randomly selected from the population. And I'm going to summarize this with only 3 parameters. Let's put them over here so I can use this space. But there's 3 of them that are important. First of all, the mean is 90. The standard deviation is 15. And little n is 25. Yeah, size 25. That's it. So I'm going to get rid of the verbal part of the question so that I can write down the calculations for this. All right. For part A, I want to find the probability that the mean of a sample is between 85 and 92. All right, so I took down my information from the introduction of the problem. Here, though, I'm not looking at the probability that a randomly selected individual is between 85 and 92. I'm looking at the probability that the mean of a sample is between those values. Very big difference. If it was just a single value, we couldn't really say anything because we don't know that this is normally distributed. But the sample means are distributed normally, so I can do that here. I just have to be careful. The mean for this distribution, the mu x bar that I'm going to use, it's the same as the regular mu, which in this case is 90. But the standard deviation that I want to use to calculate the probability is the modified one, sigma over root n. In this case, 15 divided by the square root of 25, just plugging those values in. That's 15 over 5, which is 3. All right, next I'm going to draw a picture to guide what I'm trying to do. And I think this might be the first sampling picture that we've looked at. So I am going to label this. This is not the x-axis. I don't even know if the original distribution is normal, so this probably isn't a good picture. This is the x-bar axis. All the different sample means that I can get, and it is normal as a consequence of the central limit theorem. But it's got the same mean, but it has a different standard deviation than the original one. The setup here for the picture is really the same though. The mean is 90, that's right in the middle. 85 is a little to the left of that. Let's say there's 85. And 92 is just a little bit to the right. There's 92. And I'm trying to find the probability that x bar, the mean of this randomly selected sample, is between those two values. So it's an x bar value. Let me write the probability expression, then we'll get into the calculator function. So I'm trying to find the probability that the thing is between 85 and 92. The probability that what is between 85 and 92? Not x, not an individual from the population. The sample mean, I want to know the probability that x bar is between there. How I put this into the calculator is really no different. I'm going to calculate this with a normal CDF. I need to put my lower bound 85, my upper bound 92, my mean, which is 90. I'm just going to put mu there because it's the same. Mu x bar is mu. But here, for the standard deviation, it's not the standard deviation, it's the standard deviation of the sample means. That is 3, not 15. That's why I'm very careful to use the sigma x bar notation and not sigma. I already used sigma. You could call it sigma x, but it's just, you can call it sigma. And that's the expression that I want to put into my calculator normal CDF program. Try it. You should get 0.6997 approximately. Really close to 0.7 or 70%. 70% of the sample mean scores are in this region between 85 and 92, about 70%. I've got one more thing I want to say about this picture. This is the distribution of this sample mean variable. Capital X bar represents the whole distribution, kind of the meaning of the thing. But I want to say that it's distributed normally with a mean of 90 and a standard deviation of 3. This is also a good way to keep track of your relevant parameters. It also says that it's a normal distribution, which the original one, we don't know, but very possibly it was not. The sampling distribution is normal. Let's do part B for this problem. In part B, we're going to find the value that is 2 standard deviations above the expected value of the sample mean. So the expected value of the sample mean is the average of the sample mean, or the sample mean values, but it's the mean of the means. Again, we're seeing this, we're talking about the sampling distribution, so I don't think I really need a graph for this one. 2 standard deviations above. Well, 2 standard deviations above what? You could call this expected value of the sample mean. There's a notation E of x bar, but really I think it's better to use mu x bar. The expected value is the mean. It's the value that you expect in the sense of a long-term average. We'll get back to the value in a second, but 2 standard deviations above, that means plus 2 sigma. Almost. Plus 2 sigma x bar. 2 standard deviations of this distribution. And not the original sigma. We have both of these. That's 90 was the mean, plus 2 times 3. Because 3 was the standard deviation of the sample means, and that's 96. So 96 is 2 standard deviations above the expected value, or the average of the sample means. I've got another example that uses sampling distribution, this time in a more applied sense. So the situation here for example 7.4 is the mean app engagement time is 8.2 minutes with standard deviation 1 minute. Take samples of size 60. So samples of 60 app users, and we look at the app users' average engagement time with how much time they use the app. On average, an app is used for 8.2 minutes. There's some more detail in the book, in their description, if you're curious. But for us, it's enough to recognize in this situation that the mean is 8.2 and the standard deviation is 1, and the little n, the sample size, is 60. And that's what we get out of the preamble of the problem. What are the mean and standard deviation for the sample means? So if we take samples, remember size 60, we're taking 60 different individuals. The average for the means of those samples is the same as the mean for the whole population, and that's, mu, that's 8.2 minutes. The standard deviation for the distribution of sample means is, the formula is sigma over root n. In this case, that's 1 over the square root of 60, which is 0.13. So that's the mean, that's the standard deviation. We're going to use that in the later parts. The part B of this question is kind of verbal, and I'm not going to write it. You can read it in the book if you want, but it says, what is the standard error of the mean? They're not asking us to calculate it, though. That's what this problem was about. They want to know what it means. Well, it's the standard deviation of the sampling distribution. I'm not sure how else to describe that. It's a standard deviation that talks about the spreadness, but not of the original variable app time use or app engagement. It's the standard deviation of the means of the samples of size 60. So, before I erase all of this, before I erase this part, our results from part A, I just want to summarize this with the more compact notation. The distribution of the sample means is normal with a mean of 8.2 and a standard deviation of 0.13. And those are the things that we're going to use to answer the rest of the questions. Well, in part B, that's just kind of a vocabulary question, I think. Trying to get you to connect that new standard deviation to the meaning of the old regular standard deviation. For part C, I'm going to find the 90th percentile. For the sample, well, I should probably put that whole thing. For sample mean app engagement time. Really, 90th percentile is what we're looking for. P90, in other words. It helps me to draw a picture, and again, since we're just getting started on this, I want to be careful to label that. Not the x-axis. I'm looking at the distribution of sample means here. Sample mean. It's normal, and the mean is 90. No. The mean is 8.2. 90th percentile means that 0.9 of the area is to the left of that value. I'm just going to label it K here. It's the K, just as a placeholder, a smaller symbol. But 90% of the area should be over here. You can shade it if you don't want to lose your number there. Be careful. But yeah, it's 90th percentile, so this area should be 0.9. To find that, I'm going to use the inverse normal function, which has the inputs 0.9 for the area to the left, that is. 8.2 for the mean, and finally 0.13 for the standard deviation. So not the standard deviation of app time use, standard deviation of sample mean app time use. That comes out to 8.37 minutes. So that's the answer. What it means is that 90% of the samples that we draw are going to have a mean that's less than or equal to this. That's the 90th percentile, so 90% or less than that. All right, And finally, part D. Let me leave that. For part D, we're going to find the probability that x bar is between 8 and 8.5 minutes. So this is a probability question. We're going to use the normal CDF. First, though, let's do the doodle, little picture of x bar values, which is normally distributed. My mean is 8.2. I'm going a little to the left here to 8, and a little bit to the right to 8.5. And I'm trying to find this area. In the probability notation, I'm trying to find the probability that, x is between 8 and 8.5. The probability that the sample mean is between 8 and 8.5. Not an individual, a mean from a sample of size 60. I'll find this using the normal CDF function with a lower bound of 8, an upper bound of 8.5, a mean of 8.2, and a standard deviation of 0.13. So lower bound, upper bound, mean, and standard deviation, in this case for the sampling distribution, the one that we modified. And this comes out to 0.9293. So make sure you can enter that into your calculator and get that number. This is about 93%. And that means in this range, 93% of the samples of size 60 will have a mean in this range.